Hey class, today we're going to be talking a little bit about z-scores in statistics. This is for AP Stats. And we will also be talking about the standard deviation and measures of tendency, measures of central tendency, and how they get affected when we shift or rescale our data. So if you look at your notes here, I am going to skip some things just to kind of keep this video short. So again, make sure to go to our course calendar and fill in the rest of the notes, whatever I don't go over in the video. We're going to skip down to this lovely definition box here. We have standard values or z-scores. I've put the z-score formula in two slightly different ways. We use this one. Let me do this. We use this formula, z equals x minus x bar over s divided by the square root of n for sample data. And we use this one where it's x minus mu over sigma divided by the square root of n for population data. So you'll learn in AP Stats that depending on whether your data comes from a sample or whether it comes from the entire population, we use slightly different symbols. We use those Greek letters when we have population data. Usually though, because it's a lot easier in real life to gather sample data, we'll be using the first formula there. X is going to be our data value. X bar or mu are the mean. S or sigma is the standard deviation, and N is the sample size. Now, right now, you might see this formula without the square root of n in it, because at the moment, we're not going to do anything with a sample size above 1. But later, that's going to change, and I don't want you guys to get confused. I would like you to see this formula from the beginning so that you know that the standard deviation is always divided by the square root of the sample size. The z-score indicates the number of standard deviations the data is above or below the mean. So for example, a z-score of 2.0 indicates the data value is 2 standard deviations above the mean. And similarly, a z-score of negative 0.5 indicates that our data value is half of a standard deviation below the mean. And the further the data value is from the mean, the more extreme or rare that data value is. And it could go in good or bad, depending on if you're above or below the mean. All right, so let's look at this first example. An incoming freshman scored a 76 on her math placement exam. The overall results of the exam had a mean of 82 and a standard deviation of 3. Standardize the student's math placement score and explain its meaning in context. So you'll want your calculators handy here. So I'm just going to rewrite our formula x minus x bar over s over the square root of n. And I just have an incoming freshman. So n equals 1. I only have one, a sample size of one person right now. So in this case, the square root of 1 is 1. It's not going to affect our formula. Oops. All right, so z equals her score, our x value is her score, 76, minus the mean of 82 divided by the standard deviation, which is 3 over the square root of 1. And make sure that when you put it into your calculators, I mean, right now the square root of 1 doesn't really affect it, but later, make sure that those pieces are grouped together so they stay together in the denominator, and that these are also grouped together. Parentheses are really important when you're using your calculators. All right, and then we are just going to simplify this. So 76 minus 82 is negative 6 divided by 3, so we get negative 2. So what this means in context of the problem is that she scored 2 standard deviations below the mean of her math placement. Oops. Exam. So you don't have to get too fancy with this. In the next lesson we're going to go over the empirical rule where we'll start looking at percentages of the data based on this normal curve. So this will make a little bit more sense when we get to that video. Right. The next example, I'm not going to do the entire thing because it is a little bit of a long example, but I'll start you off, especially since the 100-meter dash is a little tricky, and then I'll have you guys finish the problem. So consider three athletes' performances shown below in the three-event competition. Note that each of the competitors placed first, second, and third in one of the events. Which competitor performed best overall? So this is a really nice application of z-scores. I mean, we're going to do a bunch of work in this problem. But it's nice because if each competitor scores first, second, and third in different events, how do you determine a winner? Well, math. Math comes into play, and figuring out which events were more remarkable or more rare, extreme, away from the mean, farther away from the mean is going to help us determine that. So looking at those z-scores. So let's start with 100-meter dash. And I'm going to have competitor A, B, and C. So I want to get the z-scores for each one of these to see how they did in relation to the mean and standard deviation, which you can see here. Now, let's see, we've got z equals our data value, 10.1, minus the mean, which is 10, divided by 0.2. And then again, this is just one singular person. So over the square root of 1, you can leave that off for now if you want, but I would highly suggest you don't, because, well, later on it's going to be there, and I want you to get used to it now. All right, and then this is going to be 0.5. For competitor B, we have 9.9 minus 10 over 0.2 over the square root of 1, which ends up being negative 0.5. And for competitor C, we have 10.3 seconds minus 10 over 0.2 over the square root of 1, which ends up being a 1.5. Now, this category, unlike the shot put and the long jump, is a little tricky because if you think about running a race, the 100-meter dash, if the average is 10 seconds and someone took 10.3 seconds, did they do better or worse than the average? And because the time is larger, they were actually slower, which is worse than the average. But with a positive z-score, it looks like you're doing above average. So in this case, and I made a little note, up here. Oops, that's not what I wanted to do. Highlighter. I made a little note up here that since the 100-meter dash z's are kind of backwards, we want to negate them. And we almost never do this, but sometimes in context it's necessary. So I am going to multiply each one of these. Whoops. I am having troubles figuring out my pens this morning. All right, so I'm going to multiply each one of these by a -1. So this is going to end up being negative 0.5. This is going to be positive 0.5 because they ran the race faster than the mean at 9.9 seconds, and negative 1.5. Now you're going to do this similar thing for all the competitors in the shot put and all the competitors in the long jump. Be careful. Notice your units. That always tricks my students. So if everything is in feet, and then all of a sudden you have inches, and same with here, you're going to want to convert those inches into decimals of a foot so that you have just all feet. You don't, 27 feet and 3 inches is not 27.3 feet. So be careful. Think about what percentage or what proportion of a foot is 3 inches and use those decimals properly. So you're going to do these z-scores for each one of the other events. And then to figure out which competitor did the best, you can actually just add up all the z-scores. And the person with the highest z-score total is going to be our winner. So pretty simple solution to something that looks like a pretty complicated problem. And I will leave the rest of that up to you. All right, and then we are actually going to skip the rest of this page. So again, get it from the calendar because I wanted to go onto this page here. So when we are shifting or rescaling our data, what that means is I'm going to take all the data values, and the first thing we're going to look at is what happens if I add something. So if I have a list of data and I add 2 to every single point, but I add the same thing to every single point, what is that going to do to our measures of center or measures of location or measures of spread? So in this example, we have weight in kilograms of men, and then we subtracted 74 kilograms from each data value, and you can kind of see how that's moved from here to here on the graphs. If you look at the x-axis, the horizontal axis, the numbers have definitely changed. They've all gone down by 74 kilograms, but it's still it's still the same. It's not more spread out or less spread out. It's still the same spread. If I take all the values and just shift them, the spread, how spread out things are going to be, aren't going to change. So the measures of location, mean, minimum, Q1, Q3, median, the max, those are all going to increase or decrease by that data value that we added, or by the constant that we added to the data values. And then the measures of spread, so our range, our IQR, and our standard deviation will not change. Conversely, if we rescale our data, so if we multiply or divide all of our data pieces by a constant, it multiplies and divides everything. So measures of location and measure of spread are going to be changed. And this example is really nice because if you notice, the horizontal axis is unchanged, but you can see how the data values were more squished together on the left graph, and now they're more wide on the right graph, and they've been shifted up. The center and the min and the max, they're all shifted. So you're going to end up shifting and changing your measures of spread. So let's look at this example, and then this will be our last example for today. A convenient rule of thumb to compare SAT and ACT scores is this formula: SAT equals 40 times ACT plus 150. An admissions officer reported the following statistics about the ACT scores of 45,550 students that applied to college last year. Find the corresponding statistics for the SAT scores. So what you need to do first is kind of go down the list of this and figure out which ones are measure of location and which ones are measures of spread. The mean is just the average. It's the middle value of your, one way to determine the middle value. So that's just going to be a measure of location. Standard deviation is a measure of spread. Q1 is a measure of location. So is the median and the max, but your IQR is a measure of spread. So kind of thinking about these things first before diving into the math will save you from making a very common mistake. Now, if it is a measure of location, and you look back up here, locations increase and decrease by adding or subtracting to your data values, and they also get multiplied or divided when you multiply or divide to your data values. So for any measures of location, we're actually going to just plug them into the entire formula. So we're going to have something like 40 times 26.8, and we're going to add the 150 because multiplying and adding will change that measure of location. So when I do that, I get 1222 as my SAT score. But the next one, the standard deviation, is a measure of spread. And if you think back to how we discussed this, multiplying and dividing changes measures of spread, but adding and subtracting doesn't. So the measure of spread, our standard deviation, is going to be multiplied by 40, but it's not going to change by being added, by having that 150 added to it. So it's just going to be 40 times 3.4, which is 136. And that's definitely where students usually make their mistake, is they just plug all of these into the whole equation. You have to think about what's affecting what. Measures of location again. So we have 40 times 21 plus 150, which is 990. We have 40 times 27 plus 150, which is 1230. And another measure of location, 40 times 36 plus 150 gives me 1590. And then they sneak another measure of spread in there. So we're going to do 40 times 8, but we're not adding that 150 because adding does not affect measures of spread. We get 320. Right. And then again, you can fill out the rest of the notes based on the note keys on our course calendar. And that's it for today's lesson.